Today we're going to talk about low latency C++ and trading system. So first of all, why would you like to build such system, like an automated trading one? Well, it's a high-stakes game. Everyone wants to crack the S&P 500, or here in Germany, the DAX index, or the Euro stocks. There is a lot to make or lose, and it's a hard problem. There is a lot of people on the markets. So here, on the bottom of that slide, you can see a graph of the average daily traded volume in the past 10 years. So this is on derivatives, but it doesn't really matter too much. The general information to take from this graph is that more and more people trade on financial markets, right? So compared to like 10 years ago, on stock options, we have 3 times more volume traded. Why that? It's mostly retail flow, as we say. So like people like you and me, we have a smartphone, and we have an application where we can buy and sell stocks. And it's just much easier than before to access markets. So that means that a lot of people are there trading, and that's why it's such a hard problem, because it's both a trading problem and also a technological one, right? You need to be at the same time smart to come up with a price at which you're happy to sell or buy, because you want to make good trades. But there is a big technological aspect to it, the need of latency. So now, why do we need such latency? So I work for Optiver, and we are a market maker. And in our case, when you take the application of a smartphone, to buy or sell, if you want to buy a stock, we will be there on the other side, to sell, and vice versa. So you have to imagine that in our case, we have a few 100,000 orders out there at any given time. A bit more, I would say probably more like 1 million. But anyway, let's say 100,000 is already a lot on any instrument, to facilitate, like the trading with other people. And so let's imagine that you have this order out there, and you have a headline like this. Yeah. So you want to do a few things when you have such headline, but there is one thing that you should always do. So what is it? Yeah, indeed. I mean, you could do that, but the first thing you want to do, regardless of you being a market maker, a retail investor, any hedge fund, or any kind of like a trading actor, a financial actor, is that you want to cancel your buy orders. If you had buy orders anywhere for a certain price, now this information is obsolete, and you immediately want to cancel this. That's the first thing you want to do. After that, you want to do other things. But so that is, of course, just one example of where you need this very low latency in trading is for headlines. There are many others, of course, but that's one. So today we are going to we would like to build together such low latency automated trading system. And it's hard to cover everything in an hour talk, so I had to pick a few things, and I would like to cover with you 4 topics. The first one would be data model, second one concurrent access, then system tuning, and eventually we'd like to talk about how to measure performance. And we are going to focus on some really building, this building blocks that you can use and that effectively are being used in any low latency system. It's also time to say a bit more about me. To introduce myself, I'm David. I've been working on automated trading system for almost 10 years. So for Optiver, we're a market maker. Before that, I was working on high throughput system, so quite some overlap with the low latency side of things, but in a very different industry, in defense. So first of all, design for performance. That's what we're going to talk about today. Is it actually a good idea? So you know what Knut said, premature optimization is the root of all evil. Also a friend saying, we will make it fast if it needs to be. Well, that sounds reasonable. Myself, I consider myself a pragmatic engineer, only solving problems when they happen. So I like that. I agree with that. But what I also say, and I actually heard it also yesterday at meeting CPP during another talk on the deadline on the real-time system. Matthias said, performance should be considered at the beginning when you design a system. So yeah, performance can rarely be an afterthought. And these two quotes, they seem to contradict each other. So who agrees with Knut? Quite some people. I would expect more people to agree with Knut, but who agrees with me saying it can rarely be an afterthought? Very sweet. Oh, you agree more with me than Knut. That's very sweet of you. Well, effectively, I think both statements are correct, and they don't really contradict each other. The reason is that there are two things to look at when we consider not just performance, but in general a system: strategy and tactics. The strategy is is the approach, like the overall overarching approach, to meet a goal. So let's, for example, take as a goal, I'd like to handle 1 million of events per second, or I would like to react off a certain event with a certain latency distribution, like average less than 100 nanoseconds, standard deviation less than 10 nanoseconds. There are requirements, there are goals that you have. And so the strategy is like your overall approach to solve that problem. And now the tactics, they are your individual actions. So if I translate that to like an engineering approach, it would be like, or just when we develop, it would be like the implementation details. Like, hey, should I call reserve on that state vector? Which are the hash maps, the most efficient, and so on and so forth. And so you need both. And now back to the previous slide with like Knut saying that about premature optimization. He's definitely talking about tactics. We shouldn't immediately try to do some local optimization everywhere because in general our intuition is wrong, and we would just be complicating our software for probably nothing. So he's talking about tactics, and then when I said it shouldn't be an afterthought, talking about strategy. So today we are going to look at a bit of both. Again, on like the 4 topics that I mentioned previously, try to give you like a general strategy when it comes to a very concrete topic of building a trading system, and then look at some details still. So if we want to have a strategy on how to build such system, we need a goal. So what is our goal? How fast is fast? So 5 years ago, one of my colleagues from Optiver presented a talk at meeting CPP here, and then CPPCon, and he had a similar slide. And so if you can see on the slide that we are talking about 2.5 microseconds, on the software trading system. That's roughly where we were, or what we were talking about. So where are we nowadays? Things change a little bit. So things change always very quickly on financial markets. So what you can see on that slide on the right is what we call a trigger to target latency. Okay, what is this? A bit of a technical term that I will explain in a bit. It's on Eurex. It's the biggest European exchange. It's actually in Germany, in Frankfurt. And so what is this trigger to target latency? A trigger is when the exchange sends the event to the market participant. So the event could be a trade or a price change on a stock, for example. So these events are always sent in a very fair way, so that all the market participants receive them at the same time. And so that's what we call a trigger. And then the target is when any market participant sends an order back. So we have these 2 timestamps being taken by like a level 1 switch, like a very accurate device. A device that can very accurately timestamp packet in and out. And if you measure the difference between the 2, we see on that heat map that we approach, or that we already are around 10 nanoseconds. Okay, that's very fast. So what kind of C++ can achieve that? Well, none. So 10 nanoseconds is, by the way, taking the analogy again of the speed of light. It is roughly, the time that it takes for the light to travel between, me and I think I think just the very first row. So it's not a lot. Not sure what kind of logic we can have out there. So yeah, no C++ can achieve this. Even the new coming PCI Express standard is already too slow, way too slow for that. So what people are doing is that they have FPGAs, right? So they have VHDL, sorry, flashed on an FPGA. That's a custom board, and that's how they achieve the latency. So what are we going to talk about today? Is C++ obsolete? Well, not really. Effectively, not at all. For at least 3 reasons. So here is like a simplified but realistic diagram of trading system. And so the first reason that low latency C++ is still very much a thing is that what we saw on the previous slide is just the tip of the iceberg. It's people like to talk about these numbers because, well, they're impressive, that's true. But there is a lot going on in a trading system aside of that. And so the first reason you need low latency is, well, if you have this amazing FPGA that can send 100,000 orders in a second, let's say, you probably want to have some low latency code around it in order to receive the notification that you send something, in order to do some post checks, let's say. So that's just a safety, like a risk mechanism. The second reason is if that FPGA is able to send an order within 10 nanoseconds, it is then probably very, very simple. It's not easy. There's a lot of engineering going on in there, but it's simple. As like it sees bits, compare bits, send bits, doesn't really understand much about how to price a derivative instrument or anything. It's just not possible because that's always it's a trade-off. So what it means is that you see there is this thing that we call in industry trigger price, which is at what point do I want to buy or sell? How much do I think that this stock is worth? And so this is very much an input of this FPGA. And again, thinking about the headline that we saw before, if our friend Elon, tweet that, can imagine that our opinion about the Tesla stock is going to change relatively quickly. It's also something, there is some latency sensitivity there. So that's again something that's, all the strategy part of it, we need C++, again, low latency. And the final reason is that, as for anything, it's just a trade-off. Like there are some, and just a trade-off on like engineering requirements. There are some strategies where you really want to aim for, blazing fast, 10 nanosecond latency. Sure, then you afford, really complicated hardware on VHDL, and you go for it. But there is a lot of trading strategy where you absolutely do not need such latency. And then you use C++, like reasonably fast, like 2 microseconds, 1 microsecond, or even a bit below, and that's great. So we still have some things to talk about today. That's nice. Now I'm going to share a story on the to come to our first strategy about data modeling. A story that when I joined Optiver almost 10 years ago, there was an algorithm trading strategy that was really smart that wanted to be fast. Now you probably already encountered that in your career. There is a software A, and at some point some engineers start working on the software B. And at the beginning, B doesn't really have the goal of B is not per se to replace A. But at some point, B becomes so nice that everyone wants to work on B, and then it becomes the goal to replace A. Right? You probably recognize that. It's a typical engineering thing. Well, in that case, the problem was that our algorithm A was quite fast. Not blazing smart, but like relatively fast. And B was a software that was then designed to be much smarter, but not per se faster. And I witnessed brilliant engineers working on making this algorithm B that was very smart, right, as fast as A. A month of engineering time, were poured into that effort, and eventually, I also tried. Well, I was quite new in there, but I also gave it a shot. Eventually, it didn't work. So I was quite surprised, you know. I was like, oh, all this amazing tactics and everything, and like all this engineer trying to do that, but why didn't it work? Well, back to what we said about designing for performance, it's just that it was not designed for it. And again, there are many reasons that a certain software wouldn't be able to be fast, but the main one that I want to share with you today is about data. Is that if you don't really design your software properly, it's just going to be slow everywhere. So what's on this graph? This is like the result of a profiler, a profiling result. It's an in-house profiler that we build on the top of a Clang X-ray. So we instrument the code and we add some like timestamping. On the right, you see some function names, and on the left, not sure if you can read it, it's a bit small, but you have some time. And then there is this graph. And so the take on this thing is that, what you see in textbook when it comes to profiling and make things fast is that usually 80% of your CPU time is going to be in 20% of your code. That's awesome. Then you can just make that fast and you optimize everything. Well, that's actually in the textbook. Reality is, if you don't model properly your data, you will see something like that. And that's very underwhelming because there is no kind of hotspot. There is nothing to see. It's just slow everywhere. Okay, why is it slow everywhere? Because it cannot fit in cache. So the first strategy is all about is going to be about the size and your locality of the data. Here I put an example of some size of cache, just to get an idea of what we have on like modern processors, on the different level of cache. You know upfront when you design your system how much data you need. Like in trading, we know roughly how many stocks, for example, we are going to trade in an algo. We know how much data we manipulate, so we know like if it's going to fit in this cache, or depending on the data structure that we use, we already know upfront, or we should have an idea if it fits or not. If it doesn't, then you can choose to have more cache. You can split your application across several cores, or even across several servers. But you need to take that into account in your design. And something that is also often overlooked is that we think a lot about our code, because we love our code, but we don't really think about our colleagues' code. Right? The thing is, you need to think about the system as a whole. So like when you actually have your application on a core, you effectively share your last level on cache with your ex-colleagues, that is not there already for a few years. His code is still running on that core next to yours. And it can affect a lot the performance of your application. And so again, data model issues are, from my experience, like the main caveats that engineers fall into when it comes to designing a system. So this is like a war story from just 3 weeks ago. So I thought I would include it in today's presentation. So what you have on the x-axis is we have 2 days, and then the second day we updated the binary around 20 past 2 or so, and so the y-axis is the latency of the system, and you have just drastic change, and the change was mostly about moving data around and making sure that it was couldn't fit entirely in the cache, but just at least it would fit better. So it's not really, and if you would see the code change, it was not really anything fancy. It's just moving things around and removing things so they're more packed and together. So let's take an example. A core element of a trading system is what we call an instrument store. We're not going to what is an instrument exactly, but you can imagine it's a stock or ETF, something like that. It's a relatively small data structure. It's less than a kilobyte in general. And we have, not so many, but also not so few. We have between 1 and 10,000 of them in an algo. You want to do a lookup from time to time. You receive an ID from an external, process. You receive an ID, so you want to do a lookup. But it's not, the latency of this lookup is not too critical. You want to be reasonably fast. And last requirement is that most of the code wants to store reference to this instrument. We don't want to do within the system lookups all the time. We want to keep reference because that's just nice. It's a nice characteristic. So the instrument store, it owns all these things. So what data structure should we use with such requirements? Well, from my experience, what I see most people using is a pseudo-node map. And I like pseudo-node map. I think it has great characteristic. It's reasonably fast. It has actually stable reference on the rehash, so that's nice. But now the big downside of pseudo-node map is that all the elements, the value of the hash map, will be all over your RAM, like all over your memory. So it's like a random walk through your RAM. So often, if you watch talk from previous meetings, CPP or CPPCon about like performance or cache friendliness, you see all this benchmark about stud list and stud vector. And I think sometimes people take a bit to the first degree, the fact that we look at stud vector and stud list. And we say stud list is bad. It's not really about stud list. It's about the memory model of stud list. If you want to be fast, the memory model of stud list itself is bad. And stud-node map has the same memory model. It is a node container, which is each element is going to be allocated in a separate node. And so that's the main problem there. So like already a better solution or something that is nicer is to use a stud vector plus a map. But then this doesn't really satisfy our requirements anymore because stud vector on the resize we're going to not have a valid reference anymore, so that's not great. So my favorite solution for that is to use like a container called stable vector. I'm going to show you like the code on the next slide. It's a very, very simple container. And it is not boost stable vector. That is actually quite a bit different beast. Boost stable vector is again a node container. But just this stable vector has the same property of a vector, contiguous memory, stable pointer. Well, this one actually vector didn't have it, but it actually adds the stability to that vector. So what is it? So it's a stud vector of static vector. So I'm not sure if you're familiar with boost static vector. It's roughly a stud array with like also size, so that you know how many elements are in the array. So it's a pre-allocated vector. And so we have a vector of the static vector, and we can define a chunk size. So can you recognize, so this container is very close to a STL container. Do you recognize it? Yes, that was fast. Yeah, std-dec. So indeed, it's std-dec. The big difference with std-dec is that we can customize this chunk size. So we might say, oh, that's just a small difference. Effectively, it's big because for our locality, it actually matters. And std-dec has a very poor locality because of that. While the implementation is compiler dependent, but most compiler will take a relatively small chunk size. And as I said, the downside is that you pay a little bit of overhead when you call the at operator, square bracket, or if you use iterators. That's what I put on the right. If you profile it, you will see you can spend a lot of time shifting bits, to calculate the index. Because you don't do modulo or division because you take a power of 2. But that's, if you have slightly different requirements, if you want to walk through this container fast, you can actually do a better implementation. I mean, a different implementation than that. It's just a trade-off. So this is one of my favorite containers because it's simple. Simple things are fast, and you keep things together. So that's our strategy. We want to keep things local and small. And a great measure to check that you're doing that well is the WSS, so working set size. So not to be confused with RSS. So the RSS is usually what we allocate on touch. This is the size of your workload. And in general, we can measure it in cache lines. But effectively, there is not really any tool to measure it in cache lines. So Brendan Greggs, performance engineer from Netflix, developed a small and very nice tool to measure it, but in pages. So you might say, oh, that's not so nice because pages on cache lines are actually quite different. But let me prove you that it's actually really, really nice. So we take a benchmark like this. To be clear, we do not really care in that benchmark about the speed of execution. We are not interested in that. We just use this code in order to calculate the WSS. So we declare a stable vector, we put some integer in there, and then we do a sum. On the sum, it's just going to touch all the elements so we can calculate or see the WSS on this load. We do similarly on the pseudo-node map. Small detail, actually important detail, you see that there is a stud list there called TMP, where we push back a bunch of elements in between our endplace. We do this, and that's really important when you do such micro benchmark. It's in order to randomize the heap. Otherwise, the result you will have will be so different than what you see in production code that you need to do this. In other words, if you don't do that, for example, then on another map, all your allocation will be one after each other, and that's the problem, depending on the heap, the malloc implementation you're using, your system, you might have contiguous allocation, which will change a lot the result. And you might have that, but you might also not have that at all. So the idea is just to remove this pattern that you have when doing micro benchmarking specifically. And so this is what we get. 1 megabyte for the stable vector. So we have 100,000 in 32, so 400,000 bytes. And then we have 400 megabytes of another map of WSS. So you might say, okay, this tool is just not working. This is just absolutely not the truth. Why would we look at that? And that's why I say that it's actually quite a nice thing that it measures in pages. Because yeah, it is what it is. It measures in pages, and therefore you get a result that is, you might say, exaggerated, but it gives you a sense of the locality of your data. In this benchmark, every single in32 is on a page. So when you think about it, you're wasting actually quite some memory, right? So even if sure, if you measure in cache line, the result will be much closer. The point is you're wasting so many pages that you will suffer. Of course, from at least the main thing you will suffer will be TLB miss, because you will just do page lookup all the time. This is just with one container. So again, strategy, size and locality, you can look at WSS, but this is why it matters so much to keep things together. So now that we talked about data model, let's look at how to share this data, because it's one thing to have a process that is fast, that stay in cache. Usually, on any modern processor, we have many cores, and we want to share data. We want to communicate between this application. So one strategy, so what we want to do here is, so we receive this market data, 10 gigabit per second, so that's on the top in this market data receiver. And we want to, that's very typical of trading system, we want to fan out all this data to many different applications. Usually you have 32 core on that server, you have roughly 30 applications running on that server, and you want all of them to receive the same market data. Right. So what should be our strategy there? We want low latency, right? So average less than 100 nanoseconds. Also not so much jitter. And our strategy should target many consumers, but only one producer. And the key element is that the consumer should not affect the producer. Why that? Well, because the producer in green is getting line rate data. If any of the consumer would block it, we would start dropping packets, and then the whole system just falls apart. So they should not affect it. And so in order to do that, we have, we make the distinction between two things here. We want to have events that we want to send and state. So what do I mean exactly by that? Okay, first of all, how much data are we exactly talking about? This is on one multicast channel, just to get an idea. It's on the US market, S&P future. We receive per month roughly 300 million messages. All right, is that a lot? Is that effectively not so much? If this is really like what one application should receive, it's manageable. The problem is, it's very bursty. Again, think about the headline we saw before. It can be very quiet during the day, and then there is a headline, and this is it. Everyone reacts. So you get a million message. You get a burst of like a million message in less than a second. Back to what we were saying about events and states. So what we want to send between this application is, for example, this order book. So think about an order book as a few prices that we want to buy or sell, and you have that per instrument. We want to share this. We have two ways in our system to share this data. The first one is to send an event. So think about it as like every single new insertion or deletions, like amend of this order book we want to send. And the second one is, well, we just want to share the whole thing. We don't just want to share the state. So in one you receive a notification as well, and the other one you don't. So they are quite different. And we want to use both in our system, right? So like the strategy ABC, they want to react of this event in order to be able to send an order. So they need to receive this event in a low latency way. But then if I take the example of, at the bottom you see this trading GUI. If you just send price to a GUI, it doesn't really matter. You don't want to push 10 gigabits of price per second to a GUI. You're never going to be able to see that. You just want to have a state where you can, as a consumer, just pull the data, from time to time. So it's a push versus pull approach here. We want to look at both of them. So let's start. First of all, state. We are definitely in the domain of like locked data structure. And so we have a lot of options there. So today I'm just going to talk about one, because I think this is like the maybe not the perfect fit, but like one that is definitely underrated. Not so many people talk about it, and it's actually a great fit for trading system. Well, effectively, it's used also in Chromium, but also in the kernel, because it was originally introduced into the Linux kernel. So they were called SEQLOCK, originally fast read-write lock. And so the problem that the kernel developers had at the time is between user land and kernel land. Like as a user code, if you would do a for loop, we'd get time of the day. The time that you get, when we call the C function get time of the day is, it's updated by the kernel. And before using this lock, it was just a basic lock that was there. So the reader, the code in userland could do a denial of service where like the kernel wouldn't be able to get the lock. So I wanted to like change that. And I also wanted to be a high performance lock. So they come up with this SEQLOCK. So what is it exactly? So let's look at code. I think it will be simpler. So this is, by the way, a simplified version of the code. It's not a talk about atomics. Further in my slides, there are references in case you want to find the full C++ code. So let's not be distracted by atomics, but also let's not use this code directly in in production, because I think it compiles. So we have an atomic version here, and then we have our data. And when the writer wants to publish something, it's going to do a +1 on the version, copy the data, and +1 on the version again. Right? So on the right, I have the assembly, not of this version, but of the, let's say, the version you can find in the links at the end of my slides. And it is, as fast as you can get. You don't have actually even any locked. Well, this is on Intel, of course, on 86. You don't have any prefix locked instruction. So it's fast. So you might be wondering, where is the trick? Well, the trick is in the reader. The reader is a bit special. That's where like the smartness of that slug come from. As a reader, you read the version. If the lowest bit is set to 1, it means that there is a write in progress. And in that case, you're going to return. You failed reading the data. Otherwise, you copy the data. And then you need to recheck the version, because while you were copying the data, maybe the writer wrote something, so it could be corrupted. And therefore, you check the version again. If the version number match, awesome, it means that there was no write. Of course, in that case, T needs to be trivially couplable and using stud memcopy. That's all good. So this is quite special, and there are very interesting properties of that lock that in trading system are amazing. First of all, you see that it's based on something that we call optimistic locking, right? Why are we optimistic? Well, because we start copying the data thinking that it's not going to be changed at the same time as we read. So if you have a lot of contention, that log is going to be quite bad. But if in general you don't, then you go as fast as you can. It fits a particular pattern when you will have only a few producers. In our case, we only have one, and many consumers. In our case, on the diagram I showed, we have like 4 or 5. In real trading application, it's more like between 10 or 100. So that's quite nice. And then the last characteristic is the producer is weight-free. The producer always get the write, you always get the lock, no matter what the reader are doing. And that's also really nice. So again, for like a system where you have 100,000 of this, very small elements to share, the chances of contention are very low. And that's a great property that the more elements you have, the better it scales. In general, in system, it's the inverse. And in general, yeah, the data we share is quite small. We are talking about a few double or floats. We want to have a few prices there or volume in our system, so it works quite well. So that's one of the first strategy on how to share data. This is really nice. It's so the latency. We could measure it, but it's just the latency of memcopy. So I could benchmark it, but it's very much just benchmarking a memcopy. And then of course, on the reading side, yeah, it all depends about the main variable will be the number of producer and also the frequency rate of the producer as well, plus the number of elements. So it's actually the benchmark didn't really feel like adding one because it does depends on so many variables that depends on your system. But yeah, so with this you are as fast as you can get when it comes to sharing data. So the second one that we want to look at is events. You want to send now events with notification, not just sharing a state, let's say, on shared memory. So in order to do that, you have, again, a few options. As I said, our strategy is to have very low jitter, and we are aiming for less than 100 nanoseconds. So that discards quite a few options. TCP, well, anyway, not really a natural fit because we want to fan out, so it doesn't scale very well. UDP, why not? But you need to user space it, right? If you cannot go to kernel, you cannot afford going to kernel for this event because of our requirements. So you could user space it, but in my opinion, a lot of code to manage and quite some complexity. While actually we don't really want to send anything between server here. Our problem is just on one server. We have 32 core. We want to have some communication between these cores. So what I propose here is a queue. Very basic ring buffer on shared memory. So let's look at what kind of queue can we use here. The first one is not yet multi-consumer. So this is a typical single producer, single consumer queue. It's the one that's used in the kernel again. If you look at the IO uring, there is a queue. It looks like that. You have 2 indices, one for the writer, one for the reader. They are aligned. Okay, this is again x86, 64, so that you avoid any sharing. That's why. And so it's called a collaborative queue because the writer can, the writer knows when the queue is full, and therefore it can push back. Well, we're looking at quite a different beast here, right? We want multi-consumer. And so this read index, do we really want to have between 10 or 100 read index? Well, actually not really. That's going to scale relatively poorly. And at the same time, this pushback mechanism, do we actually want it? No, we said that we don't want a reader to compromise the writer, right? So in a system, again, when you have many, many readers, I don't want the reader to influence and to compromise, a slow reader, to compromise the trading system. That would be really bad. If a reader is slow, I just want the reader to die, right? At some point, the writer is just going to overrun it, and then we let it die. So that's good news, because relaxing that constraint, and effectively that's what we want, we can think of something that can scale better. So this is the first queue that I propose. It uses two indices, but both will be updated by the writer. Reader now, we have many of them. You can imagine that they are a bit all over, like the queue reading. The writer doesn't really know where they are. And so what's happening there is that the writer is going to update this pending index, then it's going to copy the data, and then update index. And that's kind of like how we will manage, like how we will detect that there is an overflow. Again, we align this index, 64 bytes. Okay, this is again very x86 oriented. And so this is simplified code again. The full code wouldn't really fit on the slide because we need to manage the warping of the queue, this kind of things. But this is how it looks like. And so why do we have these two indices? Is again, so the logic, kind of like the smartness in a way, is in the reader. It's because you need this pending index, and this index, you need that to check for overflow. If you would think that let's imagine you would only have index, so only one of this atomic variable, you would have to choose if you update it before or after your mem copy. And there wouldn't be a possibility for the reader to detect if there is actually an overrun. So again, very simplified code, absolutely not complete, but this is roughly how it looks like. So what kind of performance do we get with such code? So this is where we are in orange. So I benchmark against the famous Java disruptor, because that's like the reference in terms of like blazing fast queue. Also doing fan out. It's fast. And then two other comparison, I must say, not fair comparison. Boost log free queue and Moody Camel one, not fair. Why that? Because although there are SPMC queues, they are doing unicast and not multicast. So like each of the consumer is going to pick on one of the elements. It's kind of like a load balancer, like a queue that we use now. So I put them here, but I must say, not fair to compare directly these numbers. Okay, so now how do we go faster? Because that's nice, but it's always interesting to get a little bit faster, effectively, when we have a queue in Java that is in front of us. So the idea is to have less contention, right? So the reason that we are a bit limited is that here, these two indices, index and pending index, every single push and pop that we do is going to touch this index, right? The writer is going to update them, the reader is going to read them. And that is going to create, or to cause a lot of cache coherency traffic. So modern CPU all use different cache coherency protocol, but in short, the cache line will never be in an exclusive state. And that's our main bottleneck here. So the idea that we want to try is to spread out this atomic counter over, like all over the place in our queue. You kind of like a concept of elements in the queue. And so we still need some atomics, of course. I mean, some things in there in order to detect the overflow. So we need 1 bit, to see if the element is being written, and we need a version to see if the writer didn't catch up with the reader. So this is how it looks like. We start at 0, and then we publish a few elements. The fifth one, the sixth one is in progress, is in being written, and then the writer continues like that. So this is now how it looks like. We have a header with still a atomic variable, But now the big difference is that this header is only used when reader join the queue. The rest of the time, they're going to use the one per block. And so the code looks like this. Again, simplified version. Didn't want to go through all the atomics because again, it's a bit tricky. You actually need fans to implement this. But so this looks familiar. What is it? It's a SEQLOCK that we saw just a few slides before. So what we actually did is we have like this ring buffer. It's an array of lock, and we just have all our SEQLOCK there. And again, why does it work? Because the SEQLOCK properties are, optimistic locking. The more we have, the better it gets. And also, they work greatly, as we saw before, with just a few producers, in our case one, and many readers. Okay, so that looks quite promising, and it is. So we get decent like performance. Again, comparing to the other queues. Okay, one reader, we are like more than 60 million messages per second. That's really a lot. I'm not sure what we would do with that exactly. But the nice property of that queue is that even at 10 or 100 readers, we stay relatively constant, and we are actually like. We stay around like reasonable numbers. We are able to dispatch. In that case, for 10 readers, more than 20 million messages per second. So that's nice. Finish on this concurrent access. Our strategy. Low latency, low jitter. It doesn't actually also compromise the producer. That's what we have here to dispatch our event. So now let's zoom out again. A little bit. So, we looked at first, optimizing our data model in a process. Then we see, okay, how to share data between different applications. And now the last, building block or the last piece of knowledge that you need, to build such low latency system is to look at the entire server on its own. So you can run, a quick test to see if your server is properly tuned or not. This graph is a graph of each point is consecutive calls of RDTSC. RDTSC is an 86 instruction. It's reading the TSC. TSC counter is the wall clock that we have in the CPU itself. So we are reading this clock, 200 times or so. 256 here, I say. And then we are plotting the distribution. We are plotting the latency and also the standard deviation. So what we see on the graph is that we have roughly 5 or like 6 buckets of latency. Quite a high standard deviation. And so why would we get that? So this is what you should get if your system is properly configured or tuned for low latency application. Okay, what is the difference? This is code actually, just for reference. So again, calling TSC, using some boost accumulator to not do any mistakes when calculating the statistics. But so the main difference between these two graphs are C states and P states. So your CPU is optimized for power consumption. And the first one is then P states. This laptop now that I'm using just to show the slides. Well, we are not doing high performance computing with it at the moment. It's just displaying the slides. Therefore, it's probably running at 400 megahertz. It can run on a much higher voltage and frequency, up to 3 gigahertz. But at the moment, it's at 400 megahertz. And that's great. That's also like why your battery can last so long. The problem is if you have a lot of variance in the input you get in your system, back to financial markets, you can have a very, very quiet day, and then there is a headline or something is happening and you get a burst of 1 million of message. It's problematic that we are at 400 megahertz when we start receiving a burst of 1 million message. You actually you can't really afford that. Even worse than that, if the system is really not doing much, you might enter, not you, but your CPU might enter a C state, and these C states are effectively idle states, so your CPU is sleeping. So imagine the CPU is sleeping and you receive 1 million message. Well, that's not gonna fly, especially when the CPU enters a C state. Depending on the C state, without going into the details, you're going to start flushing all the different level of cache. So not just you're awake, you're all of a sudden being wake up, but also all your cache are empty, so you're going to be relatively slow processing your data. So yeah, what you wanna do if you really aim, and that's not like for every single server that you have, of course, but like for the one that needs to process at line rate, you need to tune that. You need to like disable this. Again, not on all your server, but just on the one that like need like to process 10 gigabits per second. Another common optimization is like shared, L3. So LLC is like the L3 last level of cache. It doesn't have to always be L3, but in general it is. And so here, this is like an optimization that I did a few years ago. We were changing a single line of code. So like no code change, just reorganizing application, moving them from one core to another. And so this is what we briefly talked about earlier, which is like you need to consider a system as a whole, some code, not just even C++, but like any application can run on different core, on use more or less memory, and can do what we call L3 trashing. And so by moving application between server or on different cores, and making sure that all the low latency ones are together, because in general they shouldn't use so much memory, you achieve great results like that. We were changing any code. You have much more. CPU core isolation, interrupt affinity. Between servers, you definitely, we mostly focus today about sharing data on the same server, so we're talking about shared memory. But between servers, definitely, yeah, you need to use a networking stack. There is not so much option, but you need to user space it. And then NUMA-aware code, if you allocate your memory on the far NUMA node and you access it, you're just gonna pay for nothing. And the last one, not least, like huge pages. You can get great benefit from huge pages. And again, you can enable them with what's called on Linux transparent huge pages, but they also have a little bit of a cost, actually quite an expensive cost. So in general, again, your code, if it really matters, needs to be aware about huge pages, and you should use allocator for that. Further in the slides, again, on reference, I put some links if you want to go further on this. So now the last section of this talk, again, zooming out, now you have reasonably fast application. You have also reasonably fast communication between this application, and you also did all the system tuning, so the system on its own, everything is fast, awesome. One thing that you want is to scale, right? You're going to have one trading server, and then you will have a second one, and maybe at some point you have 1,000 of them. And even if you have only 10, you still want to make sure that all the things that you measure day zero, because it's always the same, day zero, we're all very excited. So all the eyes are on the new system. But how about 6 months later, or a year later, or even 5 years later? You actually need to make sure that you stay fast. And yeah, no secret, it's not really a breakthrough here, what I'm going to say, but like you just need to continuously measure. So the same as like you would do a Google benchmark to make sure that your code is fast day zero, you need to keep on measuring in prod always. So here, this is just a graph on a dashboard. I think it just illustrates so well why you should measure in production constantly, because looking at this graph, immediately you have a few questions that come to your mind. So this, what is it? This is just a period, like a few hours, where the same application running on different exchanges or products are running, and the y-axis is the latency of our processing. But even without knowing what is this application exactly doing, because it's the same application, I can immediately, ask myself, hey, why is this top application, like this instance that is in blue, why is the latency of this one like, what is it, 2 times? Yeah, actually 4 times higher than the second one. And then why do I have a difference of 10 times, with the third one? What's happening there? So you need like this very like high level dashboards and metrics in order to have this like view, and then you can dig into like a more like system level metrics or something that is a bit more low level. So how does it work? How do you do it? Again, you need to do that when you design your application. You can't just go on every single server and run perf or something. That's you should do that as well if there is a problem, but it's a later stage. First, you want to collect all these metrics, and therefore it needs to be built in your application. And it's not really hard to do. It just needs to be usually done at the beginning of the, when you design that software. In short, what you want to do is you just want to have like, timestamping all your, not functions, let's say, but like critical part of your system, like, how long does it take to process IOs? So CPU time, on like, for example, you talked, earlier about queues. That's awesome, all these queues, but all these queues, they are fixed size. Okay, you probably are very interested about like the capacity of the queue at a given interval. Am I 10% behind, or am I 90% behind? Because if I'm 90% behind, it means that if it's a bit busier, then the consumer will be out. So you're interested in all this characteristic of your system, and then even better than looking at them, because you can only. It also doesn't really scale, right? I mean, you can look at this graph every day when you wake up with a bit of coffee, but what's even better is to have some code that actually check that, the median or the average, or you name it, the statistic that you pick for your system actually match, the expectation match reality. And so how does it work concretely? Back to our system. Again, queues. This matrix, you're going to have like a timestamp. On x86, we always use RDTSC because that's like as fast as you can get. In just a few cycles, you get a nice wall clock, and then you just, you have statistics on the difference between RDTSC, and you push that to a queue, and that's just SPSC queue, and then you have another process or thread reading this matrix, and then just publishing that to a database. And then you can visualize it. So in the previous slide, we're using Grafana to visualize that. And, come to the conclusion. We saw a few things today, but there is, of course, a lot more to say about low latency systems, also about trading system. An hour is, of course, way too short. But I hope that today's strategies and tactics, they are enough. Well, maybe not to build a full trading system, of course, but they are definitely the building blocks that we use, and that most of the companies in the industry use, so that you can be robust, which means no matter how busy things get, you can keep trading, and then also fast. Back to this latency and like why you need it. A few reference, if you wanna go further in these topics, I always put as the first reference, this famous paper from Ulrich Strepper, previous maintainer of glibc, because it's very much when it comes to data model, it is the reference, relatively old now, but still very much up to date. And then, some others, I really always like Mike Acton talk at CPPCon already 8 years ago about data-oriented design. I think it's a great talk. And on the paper about SEQLOCK, if you're interested, it's, as I said, it's quite tricky to do in C++. So, there is a full paper about, how to do that correctly in C++. So, yeah, thank you very much. I see that it's exactly 2 p.m. Yeah, I will stay around if you have questions. Thank you.